Hello everyone. I want to continue with section 5.3 on enthalpy. The learning objectives we'll talk about in this video are write and balance thermochemical equations and also calculate enthalpy changes for various chemical reactions. So let's go ahead and pick up where we left off, which was right around here. And what I want to highlight is this statement here about enthalpy. Why we like enthalpy, why by we I mean chemists in general, took the time to develop this equation is because we can equate heat flow at constant pressure to the change in enthalpy, where enthalpy is a state function, and we'll see as we develop this idea, we'll see a bit more detail in the next video, but see a little bit of it in this video. So having things that are state functions is very, very convenient, but measuring heat flow at constant pressure is very, very easy, at least relative to other things we could measure that are kind of less involved mathematically than this enthalpy equation is. But we end up with a simple equation, delta H is equal to Q at constant pressure. So that's very easy to use, and all this other stuff was to get to that point. So a couple of things that are true about enthalpy. So enthalpy is related to that idea of endothermic and exothermic that we talked about earlier. And again, it would have been maybe convenient to have this discussion prior to introducing those terms. So if you have a negative value of enthalpy, that means enthalpy is leaving the system and going into the surroundings. We call that an exothermic reaction. So negative delta H means exothermic. Positive delta H means endothermic. That means energy is going into the system as the process takes place. If we were to reverse the chemical equation, we would reverse those signs. So whatever the value of a chemical reaction is in terms of its enthalpy value, if you flip it around, you would change the sign for the enthalpy to get that new value. The next thing I want to talk about is how we show enthalpy for a reaction and what we do with that information. So we can write in a thermochemical reaction, we can write a chemical equation. So we're showing an example here. And then along with that, we can write a value for delta H. So for this particular reaction, we have delta H is equal to negative 286 kilojoules. What that means is that each time the reaction occurs as written, per mole of reaction, you have this enthalpy going on. Negative means it's exothermic. So you have negative 286 kilojoules going from the system into the surroundings each time 1 mole of this reaction takes place. So 1 mole means, in this case, 1 mole of hydrogen, half a mole of oxygen are reacted, and 1 mole of water is produced. You'll notice here that we're using a coefficient of 1/2. And when we were balancing chemical equations earlier, we said not to do that. Thermochemistry is where we get away from that, and it's because we want to have things so that we're making usually 1 mole of the product. And so to make 1 mole of the product, we might in some cases have to have fractional coefficients. So as we continue in this section, we'll see fractional coefficients continue to come up. We can take, if we're given a thermochemical equation like this, we can change it by multiplying it by something or dividing it by something. And if we do the same thing to the delta H as we do to the equation as a whole. So here we're showing this initial equation. If we multiply through by 2, so you can see how the coefficients are increasing by a factor of 2. So from 1 to 2, from 1/2 to 1, 1 to 2 again. So it's a twofold increase. We do the same thing for the delta H. We multiply it by 2. Okay, so it's twice as large here. We could also divide by 2. So we're showing that here. So a half from 1 to a half, from a half to a quarter, from 1 to a half, and then 1/2 for the delta H. Okay, so we can multiply the reaction by something. If we do, we multiply the delta H by the same thing. And then another thing to mention is that the delta H will depend on the physical state of the reactants and products. So we're mentioning that in this bullet point right here. So we have another reaction that looks very similar to the one we had before, but you'll notice that in this case we have gas, 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 and up here we had gas, gas, liquid. So we have a different physical state. And different physical states involve different amounts of energy. So we have different values for delta H in this reaction and this reaction, where the only difference between them is whether we have liquid water, water vapor here or liquid water up here. Okay, so that's the only difference. But it does change delta H, and it's important to be aware of that. So that's something you need to be on the lookout for as you're looking at these reactions, is what is the physical state, and is it the physical state that you want. So those are some things about these thermochemical reactions and how enthalpy shows up in them and what we do as we change them. Here's an example of using that kind of information. So I'll let you go through some of these examples, but what we can do essentially is we can treat that enthalpy that shows up, the delta H at the end, as being equivalent to any part of the reaction. So when we say, half a mole of O2, 1 mole of H2O, 1 mole of H2, we also have delta H is negative 242 kilojoules. So that is another conversion factor. We can take that conversion factor, we can take that number, make a conversion factor of it with any of the other numbers in the equation, which are any of the other coefficients. And so in this reaction we're showing, we can see how that works. So this is actually showing how we come up with that. Okay, so how we had a certain amount react, and we had a certain amount was used up. So dividing that amount by the number of moles gives us the kilojoules. And you'll be doing something similar to this in the lab. So kind of using the information from thermochemical reactions or developing that information from experimental data. So some additional examples here. And I wanted to talk about kind of one other thing that will be important as we continue to develop this idea. And a lot of this will go into the next video. We have something called the standard state. And it is a situation that we use as a reference point for chemical reactions. And the reason we use this is so that we can make lists of reactions and then look up information. Okay, so we define a standard state, and we're saying, okay, we're going to just write down all of the reactions at these conditions. So the standard state is you have pressure of 1 bar. If you have a concentration, it's 1 molar concentration. We don't specify temperature, but it's often assumed to be room temperature. And we also have some tables will list it at pressure of 1 atmosphere instead of 1 bar. Those are not too far off from each other, but just be aware that depending on which table you're using, you could be getting different values for that reason. So what we're going to try to do for this class is use the tables that correspond with your textbook. And, if you're looking at another source, you might get a different value. Why this is helpful is because we can tabulate values, and what that means is we can look at a reaction. We can say, okay, under these conditions, this reaction goes this way. We include a superscript of like a little zero symbol, it's actually a lowercase o, to represent the standard state that we're referring to. And some of the reasons for that we don't get into in much detail until next semester, but that's essentially saying you have kind of a pure substance. And again, that will come up next semester when we look at that. So we can look up values of reactions in various reference materials. And as we look these up, again, it's on a per mole basis, where the moles are moles as written in the given chemical reaction. So let's look at some examples. And here we're looking at standard enthalpies of combustion. Combustion, again, is a reaction with oxygen. And for most fuels that we use, this is how they work. We basically put something with oxygen, it catches on fire, and we make a bunch of carbon dioxide and a bunch of water, and we get energy out of it. So that's combustion for the most part. So you might want to know, well, which things, when you burn them, give you the most energy. And so people have made tables of that information. So here's a table listing standard molar enthalpies of combustion. So you could look at any of these, you could look them up, and what you would do is you would make a comparison. So you would say, okay, for sulfur, for this reaction, for every mole of sulfur that reacts, you would have negative 296.8 kilojoules being released. And so you see the units up here, kilojoules per mole at 25 degrees Celsius. And for every, for this one, for every half of a mole of oxygen that is reacted, you would release 283 kilojoules. So in each one of these, you can see that they are negative. Combustion reactions are mostly exothermic. So this is something that could be useful in some contexts. We are going to develop additional information that we can, this is something we could look at. Okay, look up a chemical reaction, see what it does. And that's somewhat useful, but you could have there's millions of chemical reactions. You're not going to be able to look each one up. So what we're going to develop next in the next video is a way of kind of generalizing that to make up a chemical reaction as you need it. So that's kind of where we're going with this idea. Here we're showing how we might use some information to do a calculation. So please look at that example. And then when we come back, we'll look at standard enthalpy of formation.